Welcome. Today we'll solve a mixing problem involving salt water. Here's our scenario. We have a tank containing 1,000 liters of pure water. Brine containing 0.05 kilograms of salt per liter flows into the tank at a certain rate. The solution is continuously mixed and drained at the same rate. Let's visualize our setup. Here's our tank containing 1,000 liters of water. Brine flows in from the top, and the mixed solution flows out from the bottom at the same rate. The solution is continuously mixed inside the tank. Let's analyze how the amount of salt in the tank changes over time. The rate of change of salt is equal to the rate salt flows in minus the rate salt flows out. Let's call the amount of salt in the tank at time t x of t kilograms. The concentration of salt in the output is x divided by 1,000 kilograms per liter, since the volume is constant at 1,000 liters. Now, let's write our complete differential equation. Let's say the flow rate is our liters per minute. The rate salt flows in is our times 0.05 kilograms per liter. The rate salt flows out is our times x over 1,000 kilograms per liter. Our differential equation becomes dx dt equals 0.05, our minus our x over 1,000. Let's simplify our equation. We can factor out our over 1,000 to get dx dt equals our times the quantity 50 minus x over 1,000. Separating variables and integrating, we get that x equals 50 times the quantity 1 minus e to the negative, our t over 1,000. Let's interpret our solution. At time 0, x equals 0, which makes sense since we start with pure water. As time approaches infinity, x approaches 50 kilograms. This means the tank will eventually contain 50 kilograms of salt. The parameter affects how quickly we approach this limit. A higher flow rate means we reach the steady state faster. In conclusion, we've solved a differential equation that models how salt accumulates in our mixing tank. The solution shows that the amount of salt approaches a steady state value of 50 kilograms, and the flow rate determines how quickly this happens.